Record. Welcome back to Math 160. We're going to continue looking at our Unit 7 guided notes. We left off on 7.2 regression, which was page 12. I am going to ask people to volunteer to read, so that way we're just kind of, getting into the groove, especially on a Monday morning, week 13. We are so close to the end of the semester. So how about we get this started? With regression line. I know, Lainey, you may have to go a little later. Would you start us off by just reading part A?
I would love to. Given a collection of paired sample data, the regression line, or line of best fit or least squares line, is the straight line that best fits the points in a scatter plot of paired sample data.
Perfect. I'm going to read the next part because of specific notation. So check this out. We calculate the equation for the line of best fit using the method of least squares. I want you to underline this, highlight this, something, because I want this to be familiar to you if you ever hear it again. So method of least squares. When we are finding the constants b sub 0 and b sub 1, we want to find the smallest value for the sum of the difference between your y value and y hat, right? We'll talk about that further, squared. So these are called residuals. When we calculate these values, they're called residuals, right? The difference between the estimated value and the actual data value. The method of least squares sums the squares of all vertical distance from the observed points, ordered pairs, to the regression line, the line of best fit. It finds the smallest value and then determines the constants, your y-intercept, which is b sub 0, and your slope, which is b sub 1. We are looking for the smallest differences overall. Donna, would you read both of the notes here that we have below? What are the notes here?
The line of best fit indicates what the predicted y values should be given the x value. The mean of the x values and the mean of the y values will always be a point on the line of best fit.
Perfect. Thank you so much. So we have a practice assignment here that you can actually do in Khan Academy. Again, I would urge you to click these links, play around with this. We're going to do this by hand in our notes, but it's such a great activity. I would love for you to, on your own time, try calculating and interpreting residuals. Check this out, click the link, play around with it. I think that's going to be super, super helpful in solidifying your understanding. So definitely give this one a shot at home. So at home, go ahead and take a look at that particular activity. It's actually pretty fun. I do like Khan Academy a lot. Part C, how do we even calculate it, right? How do you calculate the equation for the line of best fit? So I want you to notice a couple things here. We have a formula that helps us calculate b sub 1. According to our reading just a second ago, b sub 1 represents the slope, right? Does anyone remember the slope formula from your last class? How do you calculate slope? Do you remember? M equals
Run over something?
Okay, you're
y plus b or something like that. I don't know.
Oh no.
M1 plus M2 minus that one?
Oh man, you're getting there. We are getting there. Okay, so as a reminder, I'm going to say recall. To find the slope between 2 points.
y2 minus y1 over x1 minus x2. I mean x2 minus x1.
Yes, perfect. y2 minus y1 over x2 minus x1. Yes. Very, very nice. That's the change in your y's over the change in your x's, right? Look at the formula. It's n times the sum of the products of those coordinates minus the sum of your x's times the sum of your y's, but then divided by n times the sum of your x's squared, right? Minus the sum of x quantity squared. That's actually really interesting. So that's how we're going to calculate slope in this case. Now your y-intercept, notice the formula here. Y bar minus b sub 1 times x bar. Do you remember what x bar was? What's x bar again?
The mean.
Ah, interesting. X bar was the mean, right? So then y bar, so x bar is the mean for the x values, which means the y bar must be the mean for the y values. Okay, let me scoop this over a touch. And then of course, here's our formula. This is very similar to what we have seen in the past. What's slope-intercept form? What we learned last semester, the semester before that. What's slope-intercept form? Shout that out.
Is it y equals?
Mx plus b.
Yes, perfect. Slope-intercept form, what we're familiar with is y equals mx plus b. Notice the way in which the formula is written now. Y hat, right? Y hat represents our line of best fit. It's what's estimating what our values are going to be. For instance, if, you know, outside of that data set, outside of the x coordinates that were provided and their corresponding y coordinates. So think of this as your line of best fit, right? Right here, this equation is the line of best fit. Now you're probably looking at this and thinking to yourselves, well, why did he write it in that order? We're used to y equals mx plus b, but this is y equals b plus mx. It's okay. I don't want you to freak out about that. We know that addition is commutative, so the order of the terms really doesn't matter. The most important piece to remember is that your slope is always directly attached to your x variable, right? Mx, slope x, right? B1x. So b sub 1 represents your slope. It's directly attached to your x. Your b sub 0, think of this as like your initial value, right? B sub 0, like your initial point. This is going to represent your y-intercept, which is essentially your starting point, okay, when we think about this graphically. So I want you to keep this formula in mind as we move forward, but just remember it's from our previous knowledge, which is why we take 096 or 098 and 104 before we ever take statistics, because we need to have a solid understanding of these concepts. Sam, would you read the notes below 1 and 2?
Keep at least 3 decimal places while doing the calculations to ensure an accurate answer. And 2, when rounding off the calculated values of b of 0 and b of 1, always keep at least 2 significant digits in the final answer.
Perfection, okay? We don't want to round too much, especially as we're doing our calculations. So we want at least 3, which means 3 or more decimal places. We don't want to round too much. We want to be as accurate as possible. But then when we actually present our answers in the equation, y hat is equal to b sub 0 plus b sub 1x, we want to round, right? We want to round our b sub 0 and our b sub 1. So the suggestion here is to keep at least 2. Typically, you will see anywhere from 2 to 3 values after the decimal, okay? Typically, it's 2 to 3. You don't generally see anything greater than that. All right, let's turn the page and do some math. I hope you all have your calculators handy. We're potentially going to need that, so I would definitely go scoop that up now if you have an opportunity. Let's take a look at practice number 11. A manufacturer of automobiles wants to be able to predict. Notice the language. They want to be able to predict how many defective parts they should expect when different numbers of workers are absent. From the data below, determine the equation for the line of best fit. So first off, X represents the number of workers absent, and Y represents the number of defective parts. And these are each of your ordered pairs, right? This literally refers back to the ordered pair 3, 15, 5, 22, et cetera, et cetera, et cetera. I just wanted to write out a couple ordered pairs so that you make that connection yet again. What we want to do according to our formula from the previous page is we definitely want to square each X, we want to square each Y, and we also want to find the product of X and Y. So let's square each Y value. 3 squared, that's going to give us 9. 5 squared, 25. So we're just going to start filling in this chart. And I actually want you to do the same. So I'm going to pause the video while you fill in this chart. Okay, perfect. So what we ended up doing with our chart is, like I said before, we squared each of our X coordinates. So our X coordinates from the first column, we squared each of our Y coordinates. That was from our second column. And then we multiplied each X and Y coordinate together. So 3 times 15, 45, 5 times 22, 110. Once we calculated each of those values, we then also calculated the totals for each column. So I just literally added our values. We have 17, then we have 106, et cetera, et cetera. The last thing we need is the number of ordered pairs. N is equal to the number of data values we have here. And how many data values are we actually working with? Shout it out. We have how many points of data do we have here? What?
Is it 6?
Yes, 6 exactly. We have 6 points that we're using for our data. If that is kind of a weird idea to think about, then I want you to consider ordered pairs, right? We have our first point, which is 3, 15. Your second point, which is 5, 22. You have your third point, 07, your fourth point, 112, your fifth point, 220, and your sixth point, 630. That's okay, Susan. That's okay. And Abby, yeah, we will talk about that for sure. We will definitely discuss that later. All right, very nice. So now we're ready for our formula. So the first thing we want to calculate is our slope according to the formula. Remember, we're not using what we've used in the past because this is definitely way more sophisticated than that. So let me write down the formula for us, which is B sub 1. It's a freaking extensive formula, so you want to be really careful with how you write this. So we have N times the sum of X times Y minus the sum of your X times the sum of your Y all over N times the sum of your X squareds minus the sum of your X quantity squared. Okay, let's fill this in. B sub 1 is equal. We know that N is 6, so we're going to replace that. In your set of parentheses, it says the sum of X times Y. Remember, the bottom row are all your totals. These are all of your sums. So we want the sum of the XY column. That's going to be our 387. Ava, great question. We got 6 because that's the number of ordered pairs that we have. So here's our first ordered pair, 3, 15, our second ordered pair, 5, 22, all the way down to our last ordered pair, which is 6, 30. These represent our actual data values, right? These are our points on that scatter plot. And there happen to be 6 of them. You're very welcome. The sum of your XY is 387. So we're going to put parentheses 387. We want to be really careful not to change the formula again, right? We just want to input the values. Next, we have the sum of X. Would someone shout out that value? The sum of X?
17.
Perfect, 17. Someone else, the sum of Y.
106.
Yes, beautiful. Take a look at your denominator. And again, which is 6. Now we want the sum of X squared. What's the value there? The sum of X squared. Shout that out. Someone else?
75.
75. Excellent. And then minus, and then again, the sum of X.
289.
Wait, what was the sum of X?
17.
Yes, perfect, 17. And you are going to square it. I'll do that in a second. So I just want to show everybody each of those intermediate steps.
So if you square, would it be 289?
Yes, yes, for sure. for
Okay,
sure.
that's what I say.
You're like, I'm already ready to solve. I am doing this. I love that. I love that. My advice for all of you, do the numerator first and then the denominator. So I would literally just move from left to right, type in 6 times 387 minus parentheses 17 parentheses 106. I just punch it in exactly as I see it. My numerator is going to be 520. Same thing with the denominator, 6 times 75 minus and then 17 squared. Be careful with how you input this. And we have 161 for the denominator. And then of course, we write our answer in decimal form. I'm going to write this to 2 places after the decimal. So 520 divided by 161. Can you round this to 2 places after the decimal? What's your B sub 1?
3.23.
Yeah, 3.23. That represents your what? This is your
X scale.
No, it represents your B, like your B value for like the Y equals MX plus B. So like where it
Oh,
starts
okay.
off, your Y-intercept.
Oh, you're so close. It's not the y-intercept, it's the other one. It's your, someone else?
Slope.
Yeah, this is your slope. Here's your slope. Da, 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 da. We found the slope, which is 3.23. B sub 1 is that slope. B sub 0 is your y-intercept. And actually, we're going to calculate that in just a second. Excellent. I love this dialogue. This is fantastic. So let's go ahead and write B sub 0 is equal to, we have a formula, y bar minus B sub 1 times x bar. We know how to calculate the mean of a set of values. So y bar would be the average of all of your y's, right? So you know how to calculate the average. You say, okay, let's add up all of our values, and then we divide by the number of values we have. So to find the average of your y's, we added them up, which is 106. And we're going to divide by the number of values we have, which is 6. If you take 106 divided by 6, I would recommend we either leave 3 places after the decimal or 4. It's completely up to you. I'm going to leave 3 places after. So this gives me 17.667 if you take a look at your calculators. I'm going to round to the nearest thousandths place. X bar, same idea. Add up all your X values, which we did already, hence the chart. So when we added, we got 17. And you still have to divide by however many values we have. That's how you find the mean or the average. So 17 divided by 6 is going to give me to 3 places 2.833. And now we're going to actually plug that into our formula here to calculate the y-intercept of the line of best fit. Remember, we're creating a line so that we could predict values, right? The manufacturer wants to be able to predict the number of defective parts dependent on the number of workers who are absent. So this is our responsibility as statisticians. B sub 0 is equal to, we have 17.667, that's our y bar, minus B sub 1 is 3.23, so we're going to replace that value, 3.23, and then X bar is 2.833. We see that they are being multiplied together. Of course, you want to make sure that when you punch this in, you either input the entire expression from left to right, or you multiply first, then you subtract. So whatever you do, just be very careful with how you input into the calculator. I'm simply going to write 17.667 minus, and then parentheses, 3.23 times 2.833, and then I'm going to close it. So I find that my B sub 0, this is my y-intercept. I'm going to round to 2 places after the decimal to be consistent with my slope. And I'm going to say my y-intercept is 8.52. The last thing we have to do is actually write the equation. So the equation for the line of best fit is y hat is equal to B sub 0 plus B sub 1 x. Now remember, the only values you're going to plug in are your B sub 0, which is your y-intercept, and your B sub 1, which is your slope. That's it. The rest stays exactly the same. Think to y equals mx plus b. When you plugged in those values, you saw equations like y is equal to 2x plus 5, right? Where there's still a y and there's still an x. So our line of best fit, which will help us to predict values, is y hat is equal to 8.52 plus 3.23x. And that is your equation. Any questions on this?
Would this be on the final?
Yes. Yes, that's a great question. Yes, it will be. This is
Okay.
actually one of those kind of larger chunk type of questions. This will be on a take home, not a multiple choice.
Oh, okay.
Yeah, because you know, from our discussion, we have 2 parts for our final. Holy crap, when am I gonna get my damn haircut? So for your final exam, you have 2 parts. The first part's multiple choice, that's gonna be quick. I don't even think it would take you an hour. And then your take home part, you want to really sit with and kind of dissect and all that stuff. So you're going to have bigger chunks of questions on that take home, and regression is going to be one of them for sure.
Okay.
Cool.
Asking. I was curious.
No, I love that question. It's good. It's great to think about what's coming up, and yeah, absolutely. And there's no reason for me to play coy and be like, oh well, I don't know, you're gonna figure that out. No, I don't like that. That's not my style. I would rather just be upfront and tell you. Cool. All right, check this out. We're continuing with what we just did, right? Do you see that formula up here? Look at this. Defective parts is equal to 8.516. The Minitab output gave to 3 decimals after, to 3 places after the decimal, whereas we rounded to 2. Not that it's a big deal, right? We were just calculating by hand. Minitab calculated the exact same formula. So to be very clear, this equation here is the same as y hat, right? Your predicted number of defective parts, is equal to 8.516 plus 3.230x. That's the formula. Which means one of the success strategies that I tell students all the time is you need to write out what your X and your Y variables actually represent. Workers absent represents X. So the first thing we're going to do is we're going to actually write that. So X is equal to the number of workers absent. Okay, where Y hat is the predicted number of defective parts. Remember, you use the line of best fit to predict. So Y hat is the predicted number of defective parts. Look at each of your data values. That's from your table. So these are the values that were from your table itself. Those are the ordered pairs we use to calculate the line of best fit by hand, right? So Minitab did this for us instantly. Good. So first things first, what is the slope? What does it represent in this example? Because this section is so incredibly important, I'm actually going to walk you through this piece by piece. If something doesn't make sense or I said an explanation and you're just like, huh? You need to tell me, okay? Because you're going to see exactly this on your final exam. I need for you to be very intentional with your questions. Don't shy away from clarifying. All right, I hope everyone is paying very close attention to this. Like I said, it's recorded anyway, so you can watch it again later if need be, but please pay attention now. What is the slope? Okay, your slope is a positive 3.23. I'm going to write this over a 1. Every value can be expressed over a 1. Now, when we think about slope, I want you to think about the change in Y over the change in X. So I'm going to use some notation that may help you to remember this. If you've ever taken a science class, you've seen delta, and delta represents the change. So your numerator is the change in Y over the change in X. And that's how we calculated this slope. So change in Y, this is going to help us to write out in words what this means. So Y represents the defective parts. So I'm going to call this the change in number of defective parts. That's the numerator. X represents the change in the number of workers absent. So the change in number of workers absent. It's always helpful to label each piece of your slope so that we can write a statement that explains what's happening. Now, they're both positive numbers. 3.23 defective parts for every 1 worker absent. We're trying to think about what this means. We're thinking about slope. Slope is movement. And here's what we're going to write. What this slope is telling us is that for each additional worker who is absent, the predicted number of defective parts increases by 3.23. Positive, positive. For each additional worker absent, the predicted number of defective parts increases by 3.23. Let's write this out. So what does it represent in this example? For each additional worker who is absent, the predicted number of defective parts increases by 3.23 parts. This implies that there are less eyes, right? Less eyes on these parts. And so the number of defective parts increases. Think about what happens when you're at work and you don't have enough people there. Doesn't it tend to go towards chaos? There's so much more on your plate and you're like, damn it, if only I had coworkers who can help me get through this. So the fewer coworkers you have, the harder that process is going to be. So this should make sense. For each additional worker who's absent, the predicted number of defective parts will increase. According to the data, it's going to increase, unfortunately, because there's less hands on deck. Good. Again, as you do these problems on your own, follow the same steps that I did. I started by identifying what my variables represent. I wrote down the slope in a fraction form, and I labeled the numerator, I labeled the denominator, and then I made sense of what slope is. Slope is rise over run or fall over run. In this case, it's rise over run, so it's a change in each. What is the y-intercept? We know that the y-intercept is our b sub 0. So I'm going to write 0, comma b sub 0. And we found that b sub 0, according to the formula, because I'm going to use the 3 places, not 2 like we did, I'm going to write 8.516. Your y-intercept is 0, comma 8.516. That comes from the formula up here. Your y-intercept, there's your slope. As a reminder, according to what I wrote down initially, x represents the number of workers absent. See how I'm always labeling my values? I find that to be incredibly helpful. I would love for you all to do the same thing. Label your values. And your y represents the predicted number of defective parts. So the predicted number of defective parts. Okay, and now we want to write down what does it represent in this example and is it meaningful? What this is telling us is that when there are 0 workers absent, the predicted number of defective parts will be 8.516. I want you to be really careful when you describe slope versus an ordered pair, right? This is a point in time. With 0 workers, 8.516 defective parts. Slope is a rate of change. Slope is a rate of change. This is a constant rate of change. It is not a point in time. So we want to be really careful with how we describe each. So let's write it out. When there are 0 workers absent, the predicted number of defective parts will be 8.516 parts. It's interesting because there's a follow-up question, which is it meaningful? And you're probably thinking, is it meaningful? Well, think about, is it possible to have 0 workers absent? Sure, absolutely. You can have a full staff. You can have everybody show up to work. That totally makes sense. 0 is in our domain. Domain represents our X value. So yeah, this is totally meaningful. Let's write that out. Yes, this value is meaningful because 0 is in our domain. It makes sense as a possible value. Right? So if 0 workers are absent, we're predicting 8.516 parts being defective. Awesome. Any questions on this particular concept here? Anything that I can clarify, make more sense of? Anything that's on your mind? Are there any issues whatsoever? Wow, all right, very nice. Very, very nice. I'm hopeful that the silence means that you are feeling good about it. Okay, let's take a look at practice number 12. We're going to do the exact same idea. Again, what I would recommend is write the equation directly underneath the equation that's presented to you in the Minitab printout. So underneath weight in pounds, I'm going to write y hat equals, and we have negative 98.9 plus 4.117, and then x, right? Our height in inches, that's going to represent the other variable, that's our x. Also, what may be of benefit to you all, underneath the negative 98.9, why don't you just write b sub 0? And then under 4.117, just go ahead and write b sub 1. Why not? We might as well label everything. That way it's super, super clear what's happening. Okay, when we talk about identifying the explanatory variable or the predictor variable, what am I referring to in this case? Go ahead and shout it out. What's my explanatory or predictor variable in this case? There are two variables, two unknowns. We have explanatory and we have response. Which do you think is which?
Would it be B1?
Say that again, I'm so sorry.
Would it be B1?
Oh, I see what you're saying. Think about your variables as your unknowns. So in our equation, we only have two unknowns. We have y hat and we have x, right? So what we want to do is figure out which is which. Out of those two, which one's explanatory and which one's response? What do you think? Which one's explanatory?
So the weight pound, the weight.
You were gonna say, the height. You actually, the explanatory variable or predictor variable is actually your x. Think of that as, if you know the height, you can predict the weight, right? And that's your response. The weight is the response because that's what it's equal to. So your response variable is your y hat. Awesome. Thank you for just trying. I love this. Thank you for just, going for it. That makes all the difference. So identify the explanatory variable or predictor variable. We will write the height in inches represents our, and then you could write explanatory or predictor, whatever your heart desires. The height in inches represents our, I'm just gonna write predictor variable. The x is explaining what's happening to y. The response variable, that's your y hat, and that is your weight in pounds. So the response variable is weight in pounds. Always remember that. Explanatory X. Explanatory X. I hope that helps to serve as a mnemonic to remember that. Explanatory X. And then your response is Y. It's what it's equal to. Cool. All right. I'm going to call on you randomly, so please be prepared. Let's start with Anthony. Anthony Fortunato, what is the slope in this case?
4.117 over 1.
I love it. Notice how Anthony is writing this out as a fraction. He's already planning to label each of these pieces. So what is the slope? 4.117 over 1. Thank you, Anthony. So real quick, this 4.117, the numerator, what does this piece refer to, Anthony? The numerator.
That'd be the change in y.
Yes, this is your change in y. And instead of writing y, I'm just going to write weight if that's okay. So this is your change in weight because that is your y, right? The change in your y. And then the denominator, Anthony, would be your change in?
Height.
Yeah. Awesome. Very interesting. I want you to think about this slope. And I want you to just take 30 seconds to think about how you would write this description. So don't say anything out loud. I want you to look at this slope and consider how you would write the description. What the heck is this saying? So 30 seconds starting now. Okay, perfect. Stephanie, if you had to describe slope in words, how do you think you would go about doing that? Like, what were your thoughts in this case?
I was kind of unsure.
It's kind of trippy, right? Like, throw some
Yeah.
idea out there. What do you think?
That the height, for every 4.117 inches, there's additional weight.
Okay. What I'm going to do is, and let me also include labels real quick. That 4.117 is your change in weight, which is pounds.
Oh, okay.
And no, that's okay. This is why we do this together, right? This is why we do this together. So that, thank you for just like trying this with us. So change in height is inches. Okay. Stephanie, thank you for, giving this a shot. Back her up. How about?
Can I try?
Yeah, Donna, go for it.
So I said as the change in height increases, there is additional to weight that increases as well.
Yes, be specific. Throw numbers in there. I love what you're saying. I love it.
Can I jump in there?
Yes, absolutely.
So I kind of screwed up the way I worded it to you privately, but I said as weight increases, height increases by 4.117.
Yes, I like it. So we're introducing those values. Yes, beautiful. I'm going to tweak all of those just to, Surajini, do you want to try your hand at it?
Yeah.
Yes.
I would say for each basketball player, if the height increases by 1 inch,
Yes.
the weight would increase by 4.117 pounds.
Yes. Awesome. I love it. Okay, let me write exactly that. So for each, and I'm gonna basically take all of those and tweak just again a tiny bit, but I love the fact that we're including our values. So for each additional inch in height, right? I'm writing, you could write for each additional 1 inch in height. I just decided to write for each additional inch because that implies singular. For each additional inch in height, I'm going to include the word predicted. The predicted weight will increase by, and then of course, 4.117 pounds. Very nice. That was excellent. I love the way that we were breaking that down and kind of building on our description. Yes, perfection. Notice we include our values in our description, and our values have units. So we want to really make sure that we include those units in our description. Yes, beautiful work. Okay. Ava, what is our y-intercept in this case? What is our y-intercept?
So it's 0, comma, negative 98.9.
Yes, perfection. Notice also, as a recap, that y-intercept is the ordered pair 0, comma, b sub 0. So immediately Ava's thinking, okay, if we go back to our equation, we know that b sub 0 is negative 98.9. So I can definitely write out that y-intercept. I love that, Ava, that was perfection. As always, make sure you're labeling, okay? X is your height in inches. And your y, in this case, your predicted value, this represents your weight in pounds. Okay, now, I know that this might be an absurd statement, but I still want to know, according to this ordered pair, what is it actually telling us? Ho, would you give this a shot? Can you explain to us what you think that ordered pair is actually saying, even if it doesn't make any sense whatsoever? And just in case, how about Emma? Can you back Ho up? He might not be at his computer at the moment. I want all of you to be thinking about this.
When the height is 0 in inches, the predicted number of weight in pounds is negative 98.9.
Yes. Now, Emma, you probably felt really uncomfortable saying that, right? Because who in the hell is 0 inches tall?
Yeah.
Who is 0 inches tall and who weighs negative 98.9 pounds? Nobody, right? So we obviously can follow that up with, is it meaningful? All of us can pretty much shout no, right? But I still want us to write down what it represents. And then of course to state that it's not meaningful, because that makes no sense at all. So what does this represent in this example? Thank you, Emma, that was perfect. I'm going to write out, this represents a baseball player, because remember, we're talking about baseball players, a baseball player who is 0 inches tall will weigh negative 98.9 pounds. I find this entertaining. I'm very entertained. Obviously, this is not meaningful. This is absurd. So what we could write in this case, we could say, this is definitely not meaningful because 0 is not within our domain. And I'm also going to add to this that negative 98.9 is not in our range. Remember, we're trying to model real world problems. So having 0 inches in height show or indicate a weight of negative 98.9 pounds makes no sense at all. It is not meaningful in this particular sense, in this particular section of the domain and range. It doesn't make any sense. Now, when we turn the page, we actually still have 2 more parts pertaining to this problem. So what I would do if I were you is I would rewrite the equation on the next page. So take a look at part E. Part E says, using the equation for the line of best fit, oops, let me lower that a little. Using the equation for the line of best fit, estimate the weight of a person with a height of 62.5 inches. So again, I'm going to write y hat is equal to negative 98.9 plus 4.117x. Recall that y hat represents our weight and our x represents our height. It's always helpful to kind of jot that information down just so that we feel confident about moving forward. So using that equation, we want to estimate the weight of a person with a height of 62.5 inches. That is the information that we are given. So according to what we've done previously in our 096, 098, 104 classes, we would take the given information and we would make a direct substitution. So if you know the height, which is 62.5 inches, that's going to represent your x. You need to predict your weight using our line of best fit. So let's go ahead and plug it in. Y hat is equal to negative 98.9 plus 4.117, and then x in this case is 62.5 inches. Notice we make a direct substitution, no big deal. Go ahead and punch this into your calculators. When you have the result, please share with the entire group. And you can give me the entire value if you'd like, everything your calculator says.
I got 158.4125.
Yes, perfect. Notice y hat refers to weight. So this will be in pounds. And now we can make a statement that is associated. Perfect. Thank you so much. Let's write out. We predict that a baseball player, notice I have to use this language because I'm talking about a very specific subgroup of the population. We predict that a baseball player who is 62.5 inches tall will weigh 158.4125 pounds. Okay, we're making a prediction based on the data that we were given. Good. And last part of the day. This reads, Sarah would like to predict the weight of her newborn child who is 20 inches. Why can't she use a given regression equation? So give me some ideas as to why she can't use that equation. Throw it out there.
Too short.
Too short? Okay, tell me more.
Not a baseball player.
Well, that baby could be pretty amazing. No, you're absolutely right. That newborn child is not a baseball player. Too short. So the things that go into our minds as we consider these regression equations is we have to consider the population of interest, right? These regression equations are specific to those populations of interest. That's why Sarah couldn't use this equation to predict the weight of her newborn baby. It doesn't make sense. It's not pertaining to that same population. Good, easy enough. Let's write it out. The given regression equation is based on baseball players' height and weight. So it would not make sense to use this equation. Absolutely not. We should also note that 20 inches is definitely outside of the domain, right? We are not even looking at, newborn babies with that low of height. So 20 inches is definitely outside of our domain. So we know that 20 inches in height is outside of our domain. Good. There's only one last piece that I would like to read to you, and then that concludes our session for today. And that is the note at the bottom of this page. So I'm just going to give you an extra second to make sure you're writing out your reasoning, which is the given regression equation is based on baseball players' heights and weights. So it would not make sense to use this equation. We note that 20 inches in height is outside of our domain. There are no baseball players that are just 20 inches in height. That is crazy. Okay, take a look at the note below, and you may have to flip back to the previous page to see the actual printout. And I'll do that with you. So notice the R-SQ in the Minitab printout box. Let me turn back. Right here, you see the R-SQ? It says 51.4%. I'm going to highlight that. Let's highlight this. R-SQ is 51.4%. That is the coefficient of determination. Let's write this down. This is the coefficient of determination. And remember, we found that by taking R and squaring it. So that 51.4% represents the coefficient of determination. Let me turn back so that you can read what this means. I typed it up for you. So I'm going to turn back to the note. It is the proportion of the variation in your response variable that can be explained by the linear relationship between the predictor variable and the response variable. So for this example, and I'm going to highlight this, we can say 51.4% of the variation in weight can be explained by the height. The other 48.6% might be explained by some other factors. Okay. According to that coefficient of determination, we can say that 51.4% of the variation in weight can be explained by the height. Recall that weight is your y and height is your x. Okay. And then, of course, if you want to determine this without Minitab, you just have to square your linear correlation coefficient. And that, my friends, concludes today's session. Fantastic work. I will see you all on Wednesday. Enjoy the rest of your day, okay?
Have a good day.
Thank you too.